It all started at a child's birthday party, as most good stories do. I was a graduate student at the time, and the other parent that I was talking to was in law school. And I had been doing some research of a criminal nature, meaning I'd been doing research on criminology, not that I was doing illegal research, because that would be bad. And the person that I was talking to jokingly said, "It is better that 1,000 innocent men are locked up than that one guilty man goes free." He was totally joking, but being the social prodigy that I am, I took him seriously and I said, "No, because if you lock up the innocent man, the guilty man is going to go free. That doesn't make any sense." And we just stopped talking after that. But it gave me an idea, so I decided to model that. What would happen to a system, a culture, a community, whatever, if you were to be like super tough on crime and make sure that there is always a conviction for every crime? And I decided to model that, but not with a mechanical, mathematical model, which is what I talked about in my last video, but with a mechanical, algorithmic model. Patent pending. Maybe other people have used different terms, but those are the terms I'm going to use. So let me give a quick review of what I've talked about prior to this video. So we have statistical models and mechanistic models. So statistical models just describe associations between variables, and usually are trying to optimize the fit or prediction given some data. And you're not making any sort of restrictions on the underlying mathematical process. You usually have just B0 is equal to B1 x1 plus B2 x2, etc. And one of the points that I made before is that many different models can produce the same fit, even though they might say very, very different things about the underlying process that generates them. So those are statistical models. Nothing wrong with them except that they are super hard to falsify because they can fit anything. And I contrast that with mechanistic models, where we encode explicit mathematical rules or processes or whatever. And so we end up mathematizing exactly how our theory says the world should work. And it forces specificity, thereby increasing the riskiness of the tests. So that's where we left off. But not all mechanistic models are the same. And so I'm going to make a distinction that I don't know if textbooks talk about them. The textbooks that I've looked at don't really differentiate between them, but I'm going to. I'm going to differentiate between two types of mechanistic models. A mathematical mechanistic model and an algorithmic mechanistic model. So mechanistic mathematical models or mathematical mechanistic models, whatever, they have some sort of functional form, like an equation or possibly multiple equations. And so we tell the computer, this is the equation of the curve that I want you to fit. And then you ask the computer to adjust the parameters until it minimizes some sort of loss function or maximizes some sort of gain function or something like that. And so last time I talked about I don't know that I gave you the name last time, where I was trying to fit this exponential decay curve on photography lessons students. And I introduced this motivation model that suggests that initially, people, all they see is the advantages, and they're super likely to sign up for second class when all they see is the advantages. And then over time, they start to realize how much hard work it's going to be, and the two offset each other, and then we get this exponential decay. So that was an example of a mathematical mechanistic model. Strengths is they're super easy to compute. It might not be easy to figure out what the functional form is, but once you do, easy to compute it. And it's easy to estimate. And the limitations, at least as far as I'm concerned, besides being a little difficult to figure out what that mathematical function might look like, is that they are kind of limited. Because sometimes the things you want to model are too complex. And so what we need in those situations, when we've got a very complex system, is we need not mathematical models, but algorithmic models. So, what are mechanistic algorithmic models? Wow, that's a mouthful. Mechanistic algorithmic models. Actually kind of rolls off the tongue. Mechanistic algorithmic models. That's an iambic pentameter. So you know it's science-y. All right, so the form of it is it's not a function. It is an algorithm. What is an algorithm? An algorithm is a sequence of steps that you're telling the computer to perform. So it's a sequence of explicit rules that describe how the system evolves over time. and it is not communicated as closed form solutions. So it's probably easiest to understand when you contrast it with mathematical models. So mathematical models make statements, whereas algorithms are instructions. So just to use kind of a metaphor, like a mathematical statement might be something like maximal crispiness is obtained without burning when you bake in an oven at 350 degrees for 25 minutes. Or that is a statement, which fits into what a mathematical model is. But algorithms are like instructions. So it might be like, first you preheat the oven, then you mix the dry ingredients, then you mix the wet ingredients, then you mix the two together, then you wait for it to rise, then you punch it down, etc., etc., etc. So if you are giving instructions to a computer, you're talking about an algorithm. If you are making a mathematical statement, usually in a functional form, you are using a mathematical model. So mathematical models state what must be true, whereas algorithmic models describe what to do. So the basic idea is that we actually simulate the process that we're trying to hypothesize about. And we write a computer algorithm to perform that sequence of steps. And then we watch what happens when the computer follows the instructions. And to give you an example, I'm going to show you the algorithm that I developed based on this conversation with this lawyer. And who doesn't want to prove a lawyer wrong? I certainly do. Those blasted lawyers. All right, so I'm going to introduce the CRIM model, short for criminal recidivism and incarceration model. So this is an example of a mechanistic algorithmic model. And so the purpose of this model was to see if being tough on crime actually reduces overall criminality in a population. And to do so, it generates criminal behavior, it generates evidence, and incarcerations, and releases, and recidivism, and it basically simulates this entire process. And so I'm going to show you a simplified version of this model. It's actually quite a bit more complex that I'm going to show you, but I didn't want to get lost in the details. And if you want to see the real version, I'm working on it. It's on GitHub right now, probably a very messy version. I've been refining it over the last couple of weeks. And by the way, I have a little experience in criminology, but not much. When I came up with this idea in graduate school, my idea was to publish it, but it was way outside my area of expertise, and the person that I collaborated with ended up being pretty flaky, so never got around to publishing it. So if this is your area of expertise and you want to publish together, you let me know, because I think this is a cool model. All right, so here's the idea. First, we're going to begin by simulating a population, and the code might look like this. In this example, I'm generating 5,000 individuals, and I'm giving them each an ID here. And then I'm simulating a criminal disposition score, or their underlying criminal tendencies. And I'm also, at least initially, simulating an opportunity. And all these are vectors. So this criminal disposition score is just like everybody gets a number. And higher numbers mean they are more prone to commit crimes. And by the way, RS norm stands for random skewed normal distribution, I believe. And it ends up looking like this. And that right there represents the cutoff beyond which point people start committing crimes. And then opportunity, very similar, except it is generated from a random uniform distribution. And so higher numbers mean that the circumstances yield a much higher probability of somebody committing a crime. So maybe, for example, the circumstances are a car with its windows open and its door unlocked, inviting theft or something like that. Or maybe it's dark outside and somebody is carrying a Gucci purse or something like that. And jail length, don't worry about that. We'll see what that looks like later. And just to give you an idea of what the data set would look like at this point, it might look like this. So you get all these criminal disposition scores. Again, higher means more likely to commit a crime. Here you've got like O.J. Simpson, and here you've got Jesus, or something like that. Then what we're going to do is we're going to create a jail time score for each individual. And that also comes from a skewed normal distribution, except we're taking the absolute value. And I basically just wanted to simulate what incarceration rates look like, at least in the United States. We're pretty severe, so I think the average here ends up being a little over 5 or 5, somewhere around there. 5 years. Now, step 3, we are going to decide who commits a crime. So remember, we got those disposition scores, we got those opportunity scores. So what we're going to do is we're going to differentially weight them. So I'm going to introduce the first parameter, W, which is the weight. So if you want a system where people primarily commit crimes because of who they are, you would put W at like 0.99. And so you're saying 99% of the reason why they commit crimes is because of who they are. And then only 1% represents the opportunity. Or you could also do 50-50. So half of what determines a crime is who you are, the other half is the opportunity. And then we also have this other parameter called prevalence, which tells you the rate of crime. So if you have 100 people, and the prevalence here is 0.055, we would expect, on average, 5.5 crimes per year. And so in this simplified version of the model, we have a criminal cutoff that basically takes the aggregated score of disposition and opportunity and finds the 94.5 percentile and establishes that as the cutoff, and then says, all right, anybody higher than that has committed a crime this year. And that's all that's doing right there, is it's identifying who has committed a crime and assigning them a value of 1. Now we are going to simulate leaving evidence. And so the basic idea behind this is that we're going to assign everyone a vector, or just a string of numbers, of 1s and 0s. And for the purposes of this illustration, it's going to be 7. They have a vector of 7, where each slot might represent, oh, the guy had blonde hair. Oh, the guy's fingerprints match. Oh, the guy's DNA matches. Oh, the guy had motive. Oh, the guy had opportunity, whatever. In the simplified version, all these things are going to be weighted equally. Of course, they wouldn't in real life, but for the simulation, they are. And so let me just walk you through the code here. We're first going to identify who is not in jail, because if you're in jail, you can't commit a crime in this simulation. Of course, you can commit crimes in jail, but you wouldn't be a suspect if it happened outside of jail. And that's all we care about in this simulation. And then we're going to gather our other suspects. And so we got a pool size of 3. In other words, besides the culprit, we're going to choose 3 additional people to look at as suspects. And so that becomes our suspect pool. Then what we're going to do is we're going to generate evidence for them. And that's what this code does. And that will introduce our next parameter, which is probability of evidence, or prob evidence, which basically is what is the probability that an innocent person will leave evidence. And so if you say 0.3, that means that of that vector of 7, on average, 30% of those will be a 1 for the innocent suspects. And for the guilty suspect, it's 1 minus that. So if we go with 0.3, on average, 70% of those vectors will be a 1. And then this part, all it's doing is it is just generating the evidence. And so using random probabilities from a binomial distribution, it's going to assign 1s and 0s to the culprit vector and the innocent suspect vector. And then we're going to sum up the evidence, and then we are going to sample from the suspect pool given the evidence that we've provided. And so presumably our suspect will have a much higher evidence score than everybody else, so they have a higher probability of being selected. But there's still a chance that the innocent person will be selected. And then what we do is whoever is selected, we convict them, and then we send them to jail. And then step 5. Now I kind of lied a little bit. The last part, we don't actually send them to jail. We just say this person is going to jail. And then in the next part, we actually assign them their jail sentence and do a couple other things. But first, I need to introduce our next parameter, which is recidivism. So it is pretty well known in criminology that those who are incarcerated when they get out, they generally have higher dispositions to commit crimes. And so to simulate that, I've created this recidivism, which the way that it's quantified here and in the actual simulation, the number represents the number of standard deviations you're adding to it. And so let's say we have a standard normal distribution where the standard deviation was 1. If you put recidivism at 0.1, then what that is saying is as soon as they get out of jail, then we're going to add 1/10 of a standard deviation on average to their criminal disposition score. And this is also doing a couple other things. So this is figuring out how long they are going to jail for. So what this is saying is that if they are convicted, then we are going to assign them jail time. And then this part is basically counting down the number of years they have left in prison. And so if they are currently in jail, what we are going to look at is we're going to look at their current number and then decrease it by 1. And then finally, this last part says, all right, if somebody was just in jail and their number is now 0, we are going to release them, but we're going to add a recidivism boost. So let me just summarize the parameters in this model. We've got W, which represents how much criminal disposition factors into their committing of crimes. And 1 minus that is how much the environment plays a role, or the situation, or the opportunity. And then we got prevalence, which represents the rate of committing crimes, which is 0.055 as a default. And then probability of evidence is, again, the probability that a innocent suspect will leave evidence. And then decision threshold. Oh, that's one thing I didn't talk about, decision threshold. So you remember earlier we had this suspect pool that we randomly sampled from, but we used the probabilities, or we used the match score to do the sampling. And then after that happens, then we have a suspect that is on trial. And so what decision threshold does is it says, now let's look at their actual evidence value. And if it exceeds a certain threshold, then they are guilty. If not, then they are proclaimed innocent. And then again, we got recidivism boost, which represents the increase in their disposition score after leaving jail. And then we got pool size, which represents the number of people considered as suspects. And then finally, we've got jail sentences. So for this example, it's a multiplier on the existing jail times that, like 1.5 means whatever the raw distribution is, we're going to multiply it by 1.5, so it means higher jail sentences. So now back to this story. My lawyer friend saying I'd rather 1,000 innocent people go to jail than one guilty person go free. In a lot of ways, this is talked about as they talk about being tough on crime. And so what does that mean as far as our model? So we got a couple parameters we could adjust to be more tough on crime. One is to have longer jail sentences. So if normally we might put somebody away for 5 years, maybe we put them away for 10 years instead. And then the other thing, just think conceptually about this. If you want to be tough on crime, probably what that means is you're determined to get a conviction. Okay, how would you do that? The only way to do that is to lower the decision threshold. So in this model, I experimented with 3 situations. One where you're super tough on crime, then moderate, then very lax on crime. And again, how these are determined is by changing the decision threshold as well as how long their jail sentence is. What happens when we become tough on crime? Well, these are the results from my original study. Again, you can see GitHub for an updated version of this. In this plot, we have crimes per capita. So we got low toughness in green, moderate toughness in orange, and then in purple, we have high toughness. So we got the raw outputs that are the squiggly lines, and then we've got lowest lines just to smooth out the pattern. And so what do we find? Well, look at that, Mr. Lawyer Friend. Yeah, the tougher you are on crime, what tends to happen is you get a lot more false convictions. So you end up having more crimes per capita. Now, instead of thinking about crimes per capita, you might also think about what proportion of criminals still exist in the population. And again, we find the exact same relationship, that the higher your toughness score, the more criminals that you have that are on the loose. Again, because if you're just aiming for a conviction, you're probably going to send a lot of innocent people to prison, which means that the guilty people still go free. And it might be also interesting to look at accuracy. So we got true positives. So again, the more tough you are, the fewer true positives you have. And you also have a much higher false positive rate, as you see in the bottom there. So once again, this algorithmic mechanistic simulation shows that more toughness leads to more crime, more criminals being on the loose, and a whole lot more false convictions. So now, that's my example that I'm using, and we'll talk more about that in the next video. But why is this a mechanistic model? It's a mechanistic model because it's not like we are curve fitting like we would do with regression. And it's entirely generative, meaning the computer generates the data. So crime emerges from the rules that the model encodes. So it specifies how people behave, it specifies how the opportunities arise, it specifies how evidence is generated, how courts make decisions, and how incarceration rates affect future behavior. So with that example out of the way, let's go ahead and talk about the advantages of an algorithmic mechanistic model. Despite being in iambic pentameter, that's really hard to say fast. Algorithmic mechanistic model. Maybe I should sing it. That'll do it. All right. Advantages. Number 1, they specify the mechanism, not just the math. So these models encode the actual sequences of events. Who acts, when, under what rules. So that forces extreme specificity. And because it is so highly specific, it means it's super easily falsifiable. Because you can explicitly test and evaluate every single assumption that you make. Number 2, they generate behavior. They don't just fit curves, they generate actual behavior. Because you're not just matching an existing pattern. Instead, they produce the pattern via the rules that you feed it. And by so doing, it lets you watch how a theory unfolds over time. And you could evaluate intermediate states as well as detect contradictions. So you can easily identify problems that just simple curve fitting would hide. Number 3, they reveal emerging properties. So very often, complex systems like this, where you got recidivism loops and feedback effects and that sort of thing, they cannot be written as closed-form solutions. Whereas an algorithmic mechanistic model can naturally handle multi-agent interactions, heterogeneity of effects, interaction effects, all these sorts of things. And because of this, it enables one to detect emerging properties. So what is an emerging property? I've talked about this before, but it's when the whole behaves in a way that is not obvious from the rules that govern each of the individual parts. We've got all these different things working together, like committing a crime and determining a conviction and then setting jail times. All these different individual components, when they work together, certain behaviors emerge that you would not have predicted. So for example, one emerging property that I noticed was that in a lot of simulations, crime decreased over time, and then there was a sudden spike in crime, and I couldn't figure out why. After some investigation, I realized what was happening was that at year 1, there was a whole cohort of criminals that committed crimes, and a lot of them got sentenced to very similar jail times, let's say 5 years. And so at the end of the 5 years, they're quietly within jail building this reservoir of increased criminal disposition. And then suddenly you have this surge of crime when all these prisoners are released. And this idea behind emerging properties, there's a paper written by Roberts and Pashler, I'll leave a link in the description, where the premise of their argument was that when you're evaluating models, whether they be statistical, mathematical, mechanical, whatever, that fit isn't enough. That we can't just fit a model and say, hey, we got a good model. That one criteria you need to use to evaluate a model is the surprisingness of the model's predictions. So let me give you an example. I'm going to do this off the top of my head. I think I remember who it was. I don't remember what planet it was. But basically, there was a French astronomer by the name of Leverrier, which was trying to use Newton's equations to... he's basically trying to fit how... like the orbits of certain planets using Newton's equations. And there was one planet, I can't remember which one, I think it was Mercury. He was trying to fit Mercury, and he could not get the model to predict where Mercury was accurately. It was always off. And he said, I wonder if there is a body that is messing up the gravitational pull. And so under that assumption, he said, all right, let's hypothesize that there is a planet there that we just can't see. How big would it have to be for the numbers to actually work? And he did that. And then he pointed his telescope exactly where his math said it should be. And guess what? There was Pluto, or whatever planet it was. A previously undiscovered planet. That sort of thing is extremely surprising. To be able to say, right there, there's got to be a planet of this size. And then to turn your telescope there and find exactly what you specified. That's what Roberts and Pashler meant by surprisingness. That if it weren't for the model, the probability that you would predict that is astronomically low. Pun intended, I guess. Actually, not intended. I didn't intend it. I only realized it after I said it. Anyway, and so when you get these emerging properties, that sort of thing can happen. And it's kind of a natural byproduct. Oftentimes, you don't even plan for it. You're like, oh, wow, my algorithm is actually saying this should happen. Does that actually happen? Wow, it actually does. That's kind of cool. So this whole surprisingness is very Popper, or also last time I talked about Deborah Mayo. This idea that we want risky tests that are easily falsifiable, or another, I guess kind of the inverse of that is the surprising factor. All right, number 4 reason why these algorithmic mechanistic models are amazing. Another reason is they support real what-if experiments. So the model is a full generated world. And given that, you can alter the parameters of the model and just say, what would happen if I cut prison sentences in half? Or we really worked on rehabilitating criminals, and so their recidivism actually decreased. Or what would happen if we increased our suspect pool or decreased our suspect pool? What would happen? You could do that with these algorithmic models. So they are ideal for exploring policy decisions and what would happen when you have system-level interventions. And they allow you to evaluate the consequences of these things in real time. And let me just give another one that I didn't plan on, but I'm realizing this now as I'm going through this outline, that one of the coolest advantages of this is it makes it super easy to falsify certain assumptions. One thing that I have spent a lot of time struggling with is the disposition scores. My original model, it had that single positively skewed distribution, then I had a cutoff, and then later I said, I don't like that cutoff. I want to say that, okay, maybe everybody in the population has a small probability of committing a crime. So maybe there's some kind old gentleman that has never even said a cuss word in his entire life. Is there a situation where he might commit a crime? Sure. Maybe, for example, he might choose to destroy evidence that his son left in order to save him from a conviction or something like that. And so I tried to modify the behavior to where everybody had a probability of committing a crime. And what I discovered was that by the end of year 40, 90% of the people were in jail. And the only way that I could get it so that half the population wasn't in jail, while still allowing everybody to have at least a small probability of committing a crime, the only way I could do that is to have what's called a mixture distribution, which basically means that there are two underlying distributions. So I ended up simulating a distribution of normal people, of abstainers, people who don't commit crimes. And then I had to simulate a totally different distribution of criminals. And that was the only way I could get it to work. And that's kind of cool, because that seems to provide support for the theory that it's not just like everybody's the same. But those who routinely commit crimes are really distinct from the population. That's cool to me. Or another method of falsifiability that I discovered was that, at least in this simulation, if I had the suspect pool too high, like it seems like 3 is the sweet spot. You can only consider 3 people at one time. If you increase it beyond that, then the probability of the criminal getting selected is really low, relatively speaking. So they might become a suspect like half the time, but you still have that situation where like 90% of your population is imprisoned, mostly because of false incarcerations. Now, of course, the question is that just a product of how the math works? Or is that indicative of what happens in real life, that you don't want a suspect pool of 10 people? I don't know. It could be either, but regardless, it's like an interesting hypothesis that you can actually explore with these algorithmic mechanistic models. And then finally, 6, I think, they can model processes that are way too complex for regular mathematical mechanical models. So many real-world mechanisms are inherently procedural. They're not mathematical. Like courts don't act like equations, and juries don't act like equations. Or I saw another algorithmic model recently about like how people naturally segregate. And that's a process. It's going to be hard to describe mathematically. So many things that we might want to study require an algorithm. And when you use algorithmic models, they let you model the real mechanisms instead of like an approximation of the mechanism. So these are like really exciting, I think, really exciting ways to do research. That for certain research questions, they are exactly what you need. Of course, for other ones, they're probably not what you need. It really probably depends on the research question that you're asking. Now, the natural next question that you might be asking is, how do we evaluate these models? Fair question, and that's where it gets complicated. These models are pretty hard to evaluate, but that's what I'm going to talk about in the next video. So if you want to find out how to evaluate these models, check out the next video. And I will just say, back to the original story that motivated this birthday party conversation that I had with a lawyer. He made an offhand comment. I built thousands upon thousands of universes. And after simulating thousands of timelines, I can absolutely, with complete certainty, say that he was wrong in every single timeline. Very normal social interaction, of course. Of course, when I tried to explain why he was wrong, he lost interest when I started talking about dot products and skewed distributions and whatnot. But I'd like to think I still won that argument, that debate thing. Yeah, I win. So, I hope you will join me next time where I talk about how to evaluate these models. And then I'm going to evaluate this very model that I've created, because I'm excited about it again. And by the way, it is December 1st. Starting in 1 month, I'm going to teach my next live class. It's been a while since I've taught a live class, so if you want to interact with me, it's going to start the first Monday in January and go for the next 4 weeks. So I hope to see you there. I will leave a link in the description. If that doesn't work for you, you could always do a self-guided class, and I'll leave links to those as well. Anyway, hope you have had as much fun as I've had, and I will see you next time. Peace out.
The time has begun to record a video, cogitate, etc.
That's the deal. If only we had the knowledge of the world at our fingertips, then nobody would be ignorant. Yeah, I don't think that's how that works.
The point is to make some time for it. You don't know what you're talking about, Mr. Stats Man.
Well, I do believe I do know what I'm talking about. Ba-da-da-ba-ba-ba.
Every single good idea I've ever had has come from that.